Tags, I would end with the closing tag. Mastering dynamic programming, essential concepts, patterns and practice problems in the realm of computer science and competitive coding. Few topics rival the power and elegance of dynamic programming. This technique transforms complex recursive problems into efficient solutions by leveraging overlapping subproblems and optimal substructure properties. The goal of this comprehensive guide is to equip you with both theoretical foundations and practical skills required to solve challenging DP problems efficiently during technical interviews and algorithmic contests. Foundations of dynamic programming. Dynamic programming excels at optimizing solutions to problems containing overlapping subproblems and optimal substructure properties. These characteristics allow us to store computed results rather than recalculating them repeatedly. Recursive approaches often suffer from exponential time complexity due to redundant computations. For instance, calculating Fibonacci numbers recursively leads to O to N performance because each number recomputes previous values. Overlapping subproblems. When solving a larger problem, smaller subproblems appear multiple times. Storing solutions to these ensures they're reused instead of recalculated. Optimal substructure. An optimal solution contains optimal solutions to subproblems. If we know the best way to solve smaller instances, we can combine these to find the overall optimum. Memoization. A top-down approach storing already solved subproblem results to avoid reworked tabulation. A bottom-up approach building up solutions systematically from smallest cases upward. Space optimization. Techniques to reduce memory usage while preserving computational efficiency. Classical examples. Revisited Fibonacci sequence calculation is a textbook case illustrating the inefficiency of naive recursion. Implementing memoization reduces time complexity from exponential to linear, dramatically improving performance. The classic knapsack problem demonstrates how resource allocation decisions impact overall optimality. We explore both 0 to 1 and fractional variants of this fundamental problem in later sections. Knapsack problem variants. 0/1 knapsack. Items cannot be split, either taken entirely or not included. Requires careful selection to maximize total value without exceeding capacity constraints. Fractional knapsack. Items may be divided, allowing partial inclusion. Greedy algorithm suffices here, unlike the NP-hard 0/1 version. Longest common subsequence, LCS. This problem asks for the longest sequence common to two strings, regardless of order or continuity. Its solution builds upon comparing characters and utilizing previously computed states effectively. LCS exhibits clear signs of overlapping subproblems. By constructing a table of dimensions, n+1, x m+1, where n and m represent string lengths, we systematically fill cells representing potential subsequences. Time complexity, O, n*m, for standard implementation, though optimizations exist for space-efficient versions, O, min, n, m, space. Space reduction comes at slight cost to clarity and debuggability. Applications, DNA sequencing comparisons, text similarity checks, file differencing tools like diff. LCS remains foundational in bioinformatics and software engineering fields alike. Pattern recognition and design templates identifying familiar patterns greatly simplifies solving new DP problems. Key recurring templates emerge after working through dozens of typical exercises. Template number 1, coin change problem. How many ways to form amount X with given denominations? Uses a 1D array storing combinations possible for each value up to target sum. Template number 2, matrix chain multiplication. Determine optimal parenthesization order minimizing computation operations. Requires filling a 2D DP table where DP, I, J, represents minimum multiplications for matrices I to J inclusive. Template number 3, longest increasing subarray. Track current increasing sequences lengths while iterating through arrays. Updating global maximum as needed. Can also be modified for longest decreasing or other monotonic conditions. Always look for recurrence relations defining state transitions. Consider whether memoization, top-down, or tabulation, bottom-up. better suits your situation. Watch out for space constraints requiring further optimizations beyond basic DP tables. Advanced topics and state transitions. As problems grow in complexity, handling additional parameters becomes essential. Introducing new variables expands state definitions accordingly. Some scenarios require tracking more than simple Boolean flags, like in subset sum, or numerical counts, as seen in coin change variations. More sophisticated DP states capture richer information. State compression, reduced dimensionality of DP tables when certain parameters don't influence final outcomes significantly. Helps maintain tractable sizes even for large input sets. Status tracking, keep track of intermediate steps and decision paths. Useful for reconstructing actual solutions once optimal values are found, not just the numeric answer itself. Example case study, traveling salesman problem, TSP. Here, our state requires knowledge of visited cities and current location. Leads to O, n squared asterisk 2 to the power of n, runtime with bit mask representations for subsets. Bit mask applications efficiently represent subsets using bitwise operations. Particularly useful in TSP, dominating set problems, and other combinatorial challenges involving set membership checks. Performance analysis and optimization strategies. Evaluating runtime complexity is crucial for choosing appropriate algorithms. While DP offers significant speed improvements over brute force, poorly designed implementations may still perform sluggishly. Time versus space trade-offs. Sometimes trading increased memory usage against reduced runtime yields net benefits. Consider carefully which factors matter more in your application context. Caching layers, multiple levels of caching, including LRU caches, memory-mapped files, can supplement basic DP table storage mechanisms depending on system constraints. Parallelism opportunities. Certain DP formulations permit parallel execution through task decomposition. Identifying independent subproblems enables concurrent processing boosts. Benchmark comparisons. Traditional DP, e.g., O, n superscript 2, LCS, versus optimized approaches like sparse DP that focus only on active regions needing updates. Sparse DP concept. Only compute entries where actual changes occur instead of filling entire matrices. Reduces effective runtime though implementation complexity increases slightly. Common pitfalls and debugging tips. Many developers struggle initially with recognizing when DP applies versus alternative methods like greedy or divide-and-conquer approaches. Recurrence errors. Incorrect base cases or transition equations lead to wrong answers. Rigorous testing against small sample inputs reveals such flaws early. Index offsets. Misaligned indices cause boundary condition errors. Always double-check matrix bounds during implementation phases. Memorization scope. Overwriting cached results too soon causes incorrect reuse. Understand scope and lifetime of stored data accurately before relying on saved states. Test case selection. Choose test cases covering edge conditions thoroughly, zero-length inputs, single-element cases, duplicate values, extreme ranges. Debug strategy suggestion. Print intermediate DP table contents periodically to visualize how values evolve. Compare against manual calculations on paper for verification purposes. Visual inspection tools. Use debugging visualizers if available to watch DP table evolution dynamically. Especially helpful for multidimensional arrays and complex state transitions. Real-world algorithmic applications beyond academic settings. DP finds extensive uses in industry-grade systems dealing with complex optimization tasks daily. Data compression algorithms, LZ77/LZSS compressors, rely heavily on finding repeated substrings through dynamic programming principles. Game theory scenarios. Minimax with alpha-beta pruning implements game tree exploration via DP techniques. Chess engines benefit significantly from optimized DP-based search algorithms. Network routing decisions. Shortest path algorithms incorporate DP ideas when considering multiple criteria simultaneously: cost, latency, bandwidth requirements. Bioinformatics sequence alignment. Blast and Smith-Waterman algorithms apply DP to compare biological sequences identifying mutations and conserved regions. Stock market prediction models. Some quantitative finance models utilize DP concepts to optimize portfolio management under risk constraints. Manufacturing process planning. Optimize production scheduling with DP by evaluating trade-offs among resources, timelines, and product quality standards. Preparing for technical interviews. Technical interviewers frequently ask DP questions to assess candidates' ability to recognize patterns, design efficient algorithms, and implement clean solutions. Practice recommendations. Work through hundreds of DP practice problems categorized by difficulty levels. Focus equally on conceptual understanding and hands-on coding experience. Whiteboarding skills. Prepare to explain thought processes clearly and concisely. Demonstrate awareness of trade-offs between different implementation choices. Code quality matters. Maintain readable variable names, modular function structures, and defensive coding practices. Clean code reflects deeper algorithmic understanding. Pattern recognition training. Build intuition through consistent exposure to various problem types. Many common DP forms recur across domains despite surface-level differences. Mock interviews. Participate in simulated interview sessions with peers or mentors. Get feedback on explanation clarity and problem-solving effectiveness. Review mistakes systematically. Analyze error logs meticulously. Identify areas requiring reinforcement and create targeted study plans addressing gaps identified. Conclusion. Dynamic programming stands as one of the most powerful methodologies in computer science for tackling seemingly intractable problems efficiently. Its principles offer elegant solutions that drastically reduce time complexities compared to naive approaches. To truly master DP, consistently practice applying core concepts to diverse problem sets. Develop deep familiarity with common patterns through targeted training while remaining open to novel applications emerging across disciplines.